So in this video, I want to go through some practice problems. So we know that if we have 1 mole of a substance, we have 6.022 times 10 to the 23rd of those things, right? And then we know we could use the molar mass to figure out how many grams we have. Well, what happens if we don't have 1 mole, right? What if we want 0.324 moles? Or if we know the mass and we want to know how does that translate to the number of moles or the number of particles that we have? So we're just going to go through a lot of conversion factors using both Avogadro's number and molar mass. So before I start, I just want to do kind of a quick little review. So we'll just use carbon again as our example. So remember, carbon, our element, right, it's made up of carbon atoms. And I know that if I had 1 mole of carbon, then I would have 6.022 times 10 to the 23rd carbon atoms, right? If I had 1 mole of water, I would have 6.022 times 10 to the 23rd water molecules. If I had 1 mole of unicorns, I would have 6.022 times 10 to the 23rd unicorns. So whatever I have 1 mole of, I have that number of whatever it happens to be. Since it's carbon, we can then use carbon's molar mass to figure out what that would weigh, right? What would be the mass of that? And remember, we can just look on the periodic table. Numerically, our molar mass is the same as the atomic mass, but in terms of grams instead of atomic mass units, right? So if I had 1 mole of carbon, it would have a mass of 12.01 grams, right? The molar mass is the mass in grams of 1 mole of that substance. So what we're going to do, and we can think of these as just conversion factors if we want, right? If I have 1 mole of something, and it doesn't matter what it is, if I have 1 mole of it, then there's going to be 6.022 times 10 to the 23rd of those things, right? So what we can think of it is if I wanted to convert between moles, so let's say the number of moles, and let's actually make this nice. The number of moles and the number of items, right? Carbon atoms, molecules of water, unicorns, it doesn't matter. If I want to convert between those two things, I am going to use Avogadro's number as my conversion factor, right? So if I said we have 6.4 moles of water, how many water molecules do we have? We would use Avogadro's number as our conversion factor, right? Anytime we're going between moles of something and the number of those things, it's always going to be Avogadro's number for that conversion. The other thing that we have for a conversion is we can use molar mass, right? If we want to go between the number of moles and the number of grams, right? Remember, molar mass is the mass in grams of 1 mole of a substance. So we can use it to convert between moles and grams. So essentially, we're going to use the molar mass and Avogadro's number as conversion factors. And then we're just going to do dimensional analysis, just like we were doing in the last section when we were converting between inches and centimeters and so on. We're just going to be converting between moles and the number of items or moles and the number of grams. It's going to be the same sort of process. It's just that these are what I'm going to use as my conversion factors. Hopefully this is making a little bit of sense. If not, usually it helps when we just start doing examples. So I'm going to jump right into that. So my first one, if we have, let's say 16.04 grams of carbon, how many moles of carbon do we have? So this problem, I'm converting between grams and moles, right? We're given the mass, we want moles, and if we go back up to these two equalities that I wrote, or our two conversion factors, if I want to go between moles and grams, I'm going to use the molar mass, right? Every time we're going between moles and grams, I'm going to use molar mass. So we need to look at the molar mass of carbon. So I'm just going to go to the periodic table. I'm going to take my atomic mass. Remember, I always want to carry out at least 2 digits after the decimal point, right? And I'm going to change my units from atomic mass units to grams per mole. And I'm already writing it in the form of a fraction. If it's easier for you, by all means write it as an equality. If it looks more similar to what we've been doing and that helps, right, do it that way. I know that 1 mole is 12.01 grams. The other way to say it is that there's 12.01 grams per mole. Whichever way works better for you, but they mean the exact same thing. And then we're just going to do straight dimensional analysis, just like we had been doing before. So we're going to start with what's given in the problem. So 16.04 grams of carbon. And then remember, for units to cancel, they have to be opposite of each other. So since grams are on top, grams have to go on the bottom. The 12.01 goes with the grams, so that has to go on the bottom. And then the 1 mole goes on the top. We will cancel our units. We're left with moles, which is what we're looking for. So now it's just a matter of plugging that into our calculator. So I'm grabbing my calculator. 12.04 divided by 12.01. And I get 1.336 moles of carbon. Significant digits. This is 4 significant digits. That 0 does count, right? It's a confined 0, as does the 0 in 12.01. So 4 significant digits, 4 significant digits. I want 4 in my answer. So when I typed it into my calculator, I got 1.33555537. It goes on. But when I round to 4 sig figs, the 5 is going to round up to a 6. So let's do a few more examples. This video is really just going to be a lot of examples going through this. So our next one. How many iron atoms do we have if we have, let's say, 1.03 moles of iron? So this time what we're converting between is the number of atoms and the number of moles, right? So if we go back up to our little list here, anytime we convert between the number of things, in this case atoms, and the number of moles, we want to use Avogadro's number. So that's how we're going to convert this one. So back down to the problem. I know that there is 6.022 times 10 to the 23rd iron atoms, right, per mole. And just like we did with the last problem, if it works better, if you like it better when you write it in equality form instead of conversion factor form, by all means do it. So I know that there's 6.022 times 10 to the 23rd iron atoms in 1 mole. Right? There's that many of anything in 1 mole. So then again, just straight dimensional analysis. We're going to start with what's given in the problem. So 1.03 moles of iron. Since moles are on top, the only way for them to cancel is to go on the bottom. The 1 goes with the mole, which means Avogadro's number is going to go on the top. And cancel. I am grabbing my calculator. And I get 6.20 times 10 to the 23rd iron atoms. So significant digits, this is 3, this is 4, so I want 3 in my answer. Remember, this 0 does count as being significant because I have a decimal point. So trailing zeros are significant if there is a decimal point. Another example for us. So if we have, let's say 3.47 times 10 to the 23rd water molecules, how many grams of water do we have? So if we have 3.47 times 10 to the 23rd water molecules, how many grams of water do we have? So this one's going to be 2 steps, right? We're starting out with the number of items, right? We're starting out with the number of water molecules, and we want to go to grams. And if we go back up to our list, I don't have a way to directly do that, right? We're starting out here, right? The number of water molecules, and we want to end here the number of grams. So this one's going to be 2 steps, just like when we were doing dimensional analysis with unit conversions, right? If I wanted to go from centimeters to feet, and we were given a conversion factor from centimeters to inches, and then another one from inches to feet, we would have to do it in 2 steps. This is going to be the exact same thing. So we're going to take the number of items, we're going to convert it to the number of moles. Once I have the number of moles, we can then convert it to the number of grams. So we're going to use both Avogadro's number and the molar mass to do this problem. So I like to just write everything down so I have it. So Avogadro's number first, 6.022 times 10 to the 23rd. In this case, it's water molecules per mole. And again, if it's easier for you to write them as equalities, do it, right? 6.022 times 10 to the 23rd water molecules is equal to 1 mole, right? Same thing, just written differently. And then the molar mass of water, so hydrogen is 1.01, there's 2 of them. Oxygen is 16.00, there's 1 of them. So then we add that together, 18.02 grams per mole. So we could say that there's 18.02 grams of water for every 1 mole of water. Let's actually use these 2. Sorry, my colors are getting pretty bright here. So again, this one here and this here are the same as the 2 I just put the square around. They're just written as conversion factors. Remember, conversion factors are equalities in the form of a fraction. These here are just written in their equality form. It makes no difference which version you use. So the problem, I'm going to go start with what's given, which is water molecules. So that's the first thing I'm going to write down. So 3.47 times 10 to the 23rd water molecules. And then just straight dimensional analysis. Water molecules are on top, so water molecules are on the bottom. This is the one that has water molecules in it. So Avogadro's number is going to go down here. I'm going to run out of room, so we're going to start squishing it in here for every 1 mole. And then water molecules cancel. I'm left with moles as my unit. We don't want moles, we want grams. So we're going to go do 1 more. So I'm grabbing this. Since moles are on top, the mole is going to go on the bottom, and that means the 18.02 grams are going to go on the top. So then this is going to cancel. So our calculators. So I really, if you're not, I know I say this a few times, but I really mean it this time. I guess I always mean it, but I particularly mean it. I would get your calculator out and type this in. Please confirm that you're going to get the same answer I am. This is where folks will goof it up. They will have it right, but then they'll type the scientific notation into their calculator incorrectly, and then they're going to get the wrong answer. So before you take your first quiz, please make sure that you can type this in and get the right answer, because I will put the wrong answer as a choice. So please grab your calculator, work through this with me. If you're not going to do it right now, please make sure you do it sometime before the first quiz. If you're not sure how to use the scientific notation button on your calculator, please ask me. You want to make sure, on my calculator, I have a Texas Instruments, I'm going to use the EE button. So there's a button that has an EE on it. So when I type in scientific notation, I'm actually going to type in the 3, I'm going to hit the decimal point, I'm going to do the 4, the 7, and then I'm going to hit that EE button. And that EE button means times 10. So I'm not going to hit that. And then I'm going to hit the 2 and the 3. And then I'm going to divide it by 6.022 EE23. Do not type in the times 10. If you have a Casio, it used to be an EXP button. So it would be very similar. It's just instead of the EE button, you would use the EXP. I have seen some calculators that have a 10 raised to like the Y, some button that looks like that. You want to use that button. If you want to type it in and do a multiplication symbol and a 10 and then the caret key and raise it to the 23rd, that's fine. But then you need to put the whole entire number in parentheses. So you would have to do parentheses 3.74 multiplication symbol 1z caret key 23 parentheses. If you don't do the parentheses, when you're dividing one number by another number in scientific notation, it's not going to know that those are numbers. So what it's going to do, if you do it incorrectly, it's going to take 3.57, it's going to multiply it by 10 to the 23rd. That's no problem. Then it's going to take that answer and it's going to divide it by 6.022. Then it's going to take that entire answer and multiply it by 10 to the 23rd. It's not going to take this and divide it into this, right? It's going to take 3.47 times 10 to the 23rd. It's going to divide it by 6.022, and then it's going to multiply that entire answer by 10 to the 23rd. It doesn't know that this belongs to this because you're hitting the multiplication button. You're not hitting the scientific notation button. Hopefully this is making some sense. Usually it's a little easier to explain it in person, which is why I really want you guys to practice this. I don't want you to get it wrong because you don't know how to use your calculator. So please use your calculator correctly, get the right answer. If you're going to get it wrong because you don't understand the chemistry or the math, not because it's a technical problem with your calculator. Okay. So I'm going to grab my calculator. I'm going to do it. You're going to do it with me. If you need to pause and go grab it, go do that. And I get 10 point, I want 3 significant digits, so 10.4 grams of water is my answer. If you got like 1.04 times 10 to the something, you did what I told you to just not do. So be careful. Make sure you use the scientific notation function or put parentheses around those numbers, which is a lot more buttons to press. So I would just learn to use a scientific notation button. So 10.4 grams of water. If we had, sorry this is so long, 3.47 times 10 to the 23rd water molecules. So another example. So how many sulfur atoms are in 50.0 grams of sulfur? So I've done a few already. So for this one, I want you to actually pause the video and try it on your own, right? Oftentimes it makes perfect sense when you're just listening to me do it, but then when you get a chance to do it on your own, it doesn't always make such great sense. So please pause the video, give this one a shot, and then when you're ready to go through it, come back, press play, and we'll go through it together. So hopefully you guys did that. So this is one of the ones that is going to take a few steps, right? We're starting out with atoms and we need to get to grams, right? So we know that to go between the number of atoms, we can get to the number of moles using Avogadro's number, and then number of grams to the number of moles using our molar mass. So the same things I had written at the top, it's just that was getting messy and it's way up there now, so we'll just write it closer. So every time we're going between the number of something, in this case it's going to be sulfur atoms, and the number of moles, we're going to use Avogadro's number. And then anytime we're going between the number of grams and the number of moles, we're going to use molar mass. So we do need Avogadro's number times 10 to the 23rd sulfur atoms in 1 mole. We do need the molar mass, so I'm just going to the atomic mass on the periodic table for sulfur. So 32.07. Again, if you want to carry out more digits, by all means, but carry out at least 2 after the decimal point. Don't round it smaller than that. So that's everything we need. Start with what we're given, so 50.0 grams. Because grams are on top, grams are going to go on the bottom, so I'm going to grab this one. We'll come back and cancel. Since moles are on top, moles have to go on the bottom. So 1 mole, and then 6.022 times 10 to the 23rd sulfur atoms. So my grams are set up correctly because I cancel, and my moles also cancel. We're going to be left with atoms, which is what we're trying to solve for. So I'm going to plug this into my calculator. So 50 divided by 32.07 multiplied by Avogadro's number. And I got 9.39 times 10 to the 23rd sulfur atoms. Did you guys get the same thing, I hope? Cool. So another one, this one I'm going to add an extra step that we haven't really talked about yet. So let's say if we have, example. Let's say 175.04 grams of glucose. And glucose is C6H12O6. How many hydrogen atoms do we have? So this one's a little trickier. I am starting with grams, right? But it's grams of glucose. If we go and look at the things that we know, I'm just looking at this, the only one that has grams in it is this. So I can go from grams of glucose to moles of glucose using the molar mass of glucose. Once I get moles of glucose, I can go to the number of glucose molecules, right? It's molecules in this case, not atoms. And then for every one glucose, how many hydrogen do I have? Yeah, good, 12, right? Remember, this 12 tells me I have 12 hydrogen. So what we're adding to our list is that we can use those subscripts to tell us how many atoms we have in a molecule, right? So I know, let's just write all this down. So we need the molar mass of glucose. Let's actually do that first. So I have 6 carbon, so 6 12s times 12.01. I have 12 hydrogen, so 12 times 1.01, and then I have 6 oxygen, so 6 multiplied by 16.00, and then we'll add all that together. So I'm just typing in my calculator here. Hopefully you guys are playing along. That one we don't need a calculator for. And then 96, again, remember your calculator doesn't know significant digits, so I do need to add that 0.00 to the end of it. And then add all that together. And I get 180.18 grams per mole. So let's make a list of everything we know, right? I know that there's 180.18 grams of glucose, I'm just going to abbreviate, for every 1 mole of glucose. I also know that 1 mole of glucose contains 6.022 times 10 to the 23rd glucose molecules, or compounds. You could use compound and you'd be perfectly correct. And then I also know for every 1 glucose, there are 12 hydrogen atoms, right? For every 1 molecule or compound of glucose, I have 12 atoms, right? H12. So this one's going to be 3 steps. So I got you started. I really would love it if you would hit pause again, set up the problem, get the answer, and then hit play when you're ready to come back. So hopefully you guys did that. Again, remember, whenever we're doing a dimensional analysis problem, we're always going to start with what's given in the problem. So I'm going to start with 175.04 grams of glucose. Since grams are on top, grams are going to go on the bottom, I'm going to go to my list of equalities. The only one that has grams in it is the first one, so that's what I'm going to use. Again, I have to have the 180.18 on the bottom, so that way they cancel. Right, so those are going to cancel. And that is grams of glucose for moles of glucose. I'm just leaving it off because I am going to run out of room here. I now have moles, so we are going to, and it's moles of glucose, so this is the one I want. So 1 mole, I am going to add it back in here. 6.022 times 10 to the 23rd glucoses, molecules. I'm just going to leave it at glucose because we're going to run out of room, but those cancel. And then my last one, since moles of since glucose compounds are on top, glucose compounds are going to go on the bottom. So glucose cancels with glucose, and then 12 hydrogen goes on the top, right? So this glucose is canceling with this glucose. So calculator, 175.04 divided by 180.18. multiplied by 6.022 times 10 to the 23rd, multiplied by 12. Again, I am using that scientific notation button. And this one, if you did it incorrectly, you would actually get the correct answer because it's all on top. I'm not dividing by anything that's in scientific notation. So I ended up with, what do we want? 4 sig figs. 7.020 times 10 to the 24th hydrogen atoms. You know, and the other thing is kind of reason through, are we expecting a big answer or a small answer? So think about it, right? If I have 174 grams of something, how many atoms do I have, right? Remember, atoms are teeny, teeny, tiny, so I should have a ton of them. If you just wrote down 7.020 and didn't write the 10 to the 24th, does that make any sense? Like, would you have 7 atoms if you have 175 grams of something? Right? That doesn't make sense. If you had 7.024 times 10 to the negative 24th, like that makes even less sense. So a lot of times you can catch your mistakes if you think about the answer. If we were going backwards, if I gave us atoms and we wanted the mass, your answer should be much smaller. So kind of reason through that. So 7.020 times 10 to the 24th hydrogen atoms. So again, the new part to this problem was just using our subscripts in our chemical formula to calculate the amount or the number of a particular atom in that chemical formula. So please do some practice problems on these. These are calculations that you need to get pretty good at because we're going to be using them throughout the semester. If you have questions, please make sure to post them on the discussion board and we can talk about it at our video session.